So, good morning, everyone. My name is Vishnu Dhanda, and today I'm going to be presenting on the modeling of accurate geometries for finite element analysis of 3D printed composite parts. My supervisors are Nick, Sam, and Dr. Joanna Wong, and I'm from the Laboratory of Engineering Materials. So, what is additive manufacturing? This is a process whereby material is deposited layer by layer. For example, the 3D printing you see right there. Advantages of this is rapid prototyping, so you can get from start to finish really quick. Manufacturing of complex geometries, like the one you see right there, and lower cost. It's very cheap. So at the Laboratory of Engineering Materials, we focus on additive manufacturing of continuous fiber reinforced composites. Composite is basically a combination of two materials with different chemical and physical properties. And when you do this, you get these materials with incredible properties, which combine these different chemical and physical properties. We did with carbon fiber composites. So that's just carbon fibers enclosed in a thermoplastic matrix. Applications of what we're dealing with is, well, aerospace. So our lower pressure vessels and like Falcon 9 rockets are made out of composite. We have prosthetics, so biomedical applications, very cool. And we have like sporting applications. So that's like a mountain bike rocker. You may see it in like Formula One cars, completely composite essentially. Very cool. Our problem is when we print these composite parts, we end up with these outer plane deformations that you see in red right there, because you're putting one toe over another toe, and these aren't really aligned, so you end up with the outer plane deformation. Another thing is fiber bridging, because you have inelastic nature of these carbon fibers, but the thermoplastic is pretty elastic, so you end up with fiber bridging, because nothing really wants, the carbon fibers really don't want to stretch. These negatively affect mechanical strength. What's been done? So these are pictures from like several research papers. What you find is that no one really models these accurately. So no one's modeling the outer plane deformations that's seen. Neither is no one modeling the fiber bridging that's occurring. And the end result of this is you end up with really poor FEA. So the picture you see at the bottom there, that's FEA being done for one of these parts. And you end up with really bad results for your FEA. Not very, very good because you don't have accurate geometries. So we developed a draping analysis method in the Rhino CAD system using a Grasshopper physics engine. And think about this as like just taking a cloth and dropping it over a irregular shaped object. The cloth would sort of take that shape, and that's exactly what we did with these carbon fiber toes. Uh, we we ended up getting something that looks like this. And this is like one small nodal region of a massive part. And what you can see is that we have an outer plane deformation right there. And that outer plane deformation is actually very similar to what's being seen in the real world. So we have the same degree of outer plane deformation, moreover. Another thing is we have fiber bridging model, which is very, very cool. Like no one else is modeling fiber bridging. We got it right here. The fiber bridging is resulting in voids, which are basically like massive air gaps, and that's what causes your poor mechanical strength, actually, in addition to the fiber bridging. One more thing about the fiber bridging is that the carbon fibers is one of the materials where you only have strength in the direction of its travel, essentially. So when you have outer plane deformations, you end up changing the direction of travel, which negatively affects your mechanical strength. As you can see in that microscope image right there, our fiber bridging is very, very similar to what's being seen in microscope images. So we're getting a really, really accurate model. We also developed a way to export these meshes that were made into Abacus, which is a finite element analysis software, which is really famous. We also have this developed for ANSYS, but we're going with Abacus. We are starting to perform finite element analyses on these meshes, and the nice thing about this is we can rapidly vary our geometry. So we don't need to manufacture these geometries to actually check how good they are. We can actually just check how good they are, see if it's going to work, it's going to take our loading scenarios, and go ahead and then manufacture them. So we're making these, the finite element analysis that we're currently carrying out is being compared to mechanical testing, and we're getting extremely results. I would like to finally, acknowledgements. I would like to thank Laboratory of Engineering Materials, specifically Nick Elderfield, the PhD candidate, who has really really helped me, in addition to Santa Fig, which is also a PhD candidate now. And I've had the guidance of both of these, in addition to both of them, and in addition to Dr. Joanna Walk. Finally, I want to thank the Schulich School of Engineering, who funded this research. I'm guessing we don't have questions because we're in Zoom, but thank you. And that is my contact information.